this computer. Okay, so I believe I am now recording. Are you still hearing me? Okay. So right click, you can see the laser pointer option. Oh yeah. Okay, thank you very much, whoever that was. Okay, here's the thank you. All right, let's do this again. Now we're recording. Deoxygenated blood flows from the brain and from the body to the right atrium. This is happening between heartbeats. The heart is at rest. Blood is returning to the heart, to the right atrium, and it flows through the tricuspid valve into the right ventricle. At the same time, the heart is still at rest. Oxygenated blood is returning to the heart from the lungs via the pulmonary veins to the left atrium, and it flows through the bicuspid valve to the left ventricle. So during this period of between heartbeats, the heart is refilling on the right side and on the left side. Now the heart beats, and we will talk about how the heart beats in just a few moments. But the contraction of the heart, the contraction of the myocardium, increases the pressure in the right and the left ventricle. That pressure in the right ventricle closes the tricuspid valve, opens the aortic semilunar valve, and forces blood from the right ventricle into the pulmonary arteries, where it goes to the lungs. At the same time, the left ventricle contracts, the myocardium of the left ventricle contracts. The pressure in the left ventricle increases. That pressure increase closes the bicuspid valve and opens the aortic semilunar valve and forces blood from the left ventricle into the aorta, where it flows to the head or to the body. So that's the story of blood flow through a heartbeat. Blood returns between the beats, then the heart contracts and the pressure builds up in the right and the left side, and the blood on the right, in the right ventricle is forced through the pulmonary, I think I might have said the wrong word here before, the pulmonary semilunar valve into the pulmonary artery, and the blood on the left ventricle is forced through the aortic semilunar valve into the aorta, where it goes to the head or to the rest of the body. So now our goal is to understand the heartbeat. That's what we're trying to do now. Well, how does the heart beat? The heart beats because it has an electrical system intrinsic to it. I'm just going to check. I'm going to check the chat for a moment to make sure that there's no more questions. So Sophie told me about the pointer option. I I believe I am recording because I'm getting a little red recording button. So I hope that it's recording, but we're going to continue on now. Just had a question. When I look at the chat like this, do you all see my chat box, or are you still seeing the slide? Tell me, nod your head if you're seeing the chat box. Shake your head if you're seeing the slide. Okay, good. Thank you very much. All right, so let's look at the slide. So here is a cartoon of the heart, and we're going to be focusing on pacemaking and electrical pathways. Here is a key point. The intrinsic pacemaker of the heart is in a part of the heart called the sinoatrial node. That is the part of the heart that sets the pace. And we'll talk about how it does that physiologically in a minute. The rest of the heart follows the pace set by the sinoatrial node, unless there is some disease state. So electrical signals in the sinoatrial node are transmitted throughout the rest of the heart because, remember, all the heart cells are connected to their neighbors at gap junctions, at the desmosomes. So pacemaking in the sinoatrial node spreads throughout the atria, and then it is going to spread through a specialized electrical pathway through the ventricles. So let's start with in the next slide with how the sinoatrial node paces. Well, okay, so not quite the next slide. So this slide shows the sinoatrial node beats first. Electrical activity spreads throughout the atria. That's what this yellow is supposed to signify. So electrical signaling spreads from the sinoatrial node throughout the atria. Then the electrical signals, and you know electrical signals are action potentials, which we'll talk about in a moment. Action potentials spread from the atria throughout the ventricles in this well-organized fashion, from the atrioventricular node through the interventricular septum, then throughout the ventricles. And then over here is relaxation. But let's look at the spread of excitation. SA node, atria, AV node, septum, and the rest of the ventricles in that well-organized pattern. That pattern is going to generate the electrocardiogram, but we're going to talk about that next week. So now let's figure out how the heart does this. I'm going to skip this slide and come back to it. So this is a slide that shows the action potentials in the pacemaker cells of the SA node. By pacemaker, what this means is that these cells spontaneously fire action potentials. They do not require the nervous system to generate an action potential. And they do that because they don't really have a steady resting membrane potential. So let's get oriented. This is the membrane potential as a function of time. The membrane potential at rest, this is negative. So this membrane potential is negative, but it's not steady. It slowly depolarizes. Why does it slowly depolarize during this, quote, resting period? It slowly depolarizes for three reasons. One is that the potassium channels that were responsible for the repolarization of the previous heartbeat close. So you know that potassium channels are necessary for maintaining a negative membrane potential of a resting cell. But if the channels close, the force that is holding the membrane potential negative is decreased. And so the closing of the channels allows the membrane potential to creep up. Why does it creep up? It creeps up because we have channels called IH channels that are opened at negative membrane potentials. The H actually stands for hyperpolarization. So these are channels that are opened by hyperpolarization, and they are sodium permeable. So sodium entering and less potassium leaving causes the membrane potential to creep up, to depolarize. Sodium entering, bringing in positive charges, and less potassium leaving, less potassium carrying out positive charges or leaving behind negative charges, less potassium leaving, more sodium entering, the membrane potential gets less negative, which is what's happening here. Eventually, so now we depolarize, and the depolarization opens voltage-gated calcium channels. Voltage-gated calcium channels allow calcium to enter. And so here is, again, a positive charge entering, which causes further depolarization. Eventually, we get to a threshold where enough calcium channels cause enough depolarization to open more calcium channels. It's the same kind of feedback loop that the sodium channels use for the nerve and muscle action potential. Depolarization opens voltage-gated calcium channels, calcium enters, more depolarization. More depolarization, more channels open, more calcium entry, more depolarization. So we go from a slow dribble influx to a rapid calcium influx. It's the same story as the nerve action potential. It's just that it's calcium doing the depolarization instead of sodium. This is an action potential. Eventually, the calcium channels inactivate and the potassium channels activate, and that causes repolarization. Remember, potassium exiting through potassium channels leave behind a negative charge. More negative charges left behind as the potassium channels open, more negative, and we end the action potential. And then we start all over again. So the point here is that pacemaker cells spontaneously depolarize through these mechanisms here, fire action potentials that are calcium channel based instead of sodium channel based, repolarize by potassium channels just like nerve, and then do it over and over and over again, approximately 1 time a second for as long as you live. questions about the pacemaker mechanism. So in the SA node, this is the mechanism for why the cells spontaneously fire action potentials. Now the question is, why do these action potentials spread throughout the heart? They spread throughout the heart because there are gap junctions between the cells. And so if this cell fires an action potential, that depolarization spreads throughout these gap junctions from one cell to the next cell. And so if this cell fires an action potential, this cell receives the depolarization and fires an action potential. So they are coordinated. They are connected one to the next, to the next, to the next in a network of gap junction dependent connections. So I'm going to go back one more slide. So the sinoatrial node fires action potentials that I've just described the mechanism of, and now it's spreading. Now I'm going to talk about how it's spreading throughout the atria in the next slide. It's spreading because of gap junctions to neighboring cells. And now, I'm sorry, I'm going to go back 2 slides. Now we want to talk about the action potentials of these muscle cells here and here. The sinoatrial node are pacemaker cells, but they don't have a very strong contraction. The muscle cells of the atria, and more importantly, the ventricles, have a different action potential that are not pacemakers, but are contractile. This is easy compared to what you just covered. The muscle cells of the atria and the ventricles is very negative. The resting membrane potential of the atrial and ventricular muscle cells is very negative. Why? Because they have a lot of resting potassium channels. These cells would stay at this negative resting membrane potential forever, but they get depolarized. Why do they get depolarized? Because their neighbor got depolarized. Why did their neighbor get depolarized? Well, we're working our way backwards because maybe their neighboring cell was a sinoatrial nodal cell that spontaneously fired an action potential. So I'm going to go back again. So if this cell spontaneously fires an action potential, it's depolarizing, and now the neighboring cells are receiving that depolarized information, and that depolarization triggers a contractile action potential. So the depolarization activates voltage-gated sodium channels, just like nerve action potentials. So now it's that positive feedback loop of the nerve voltage-gated sodium channels. Depolarization opens channels, sodium influx, more depolarization, more open channels, more sodium influx, more, etc. The all or none depolarization of the cell. Now in the heart muscle cell, just like in the nerve cell, the voltage-gated sodium channels inactivate. But now, like in the nodal cells, but unlike in nerve cells, there are voltage-gated calcium channels in these heart muscle cells. The depolarization that was triggered by voltage-gated sodium channels opens voltage-gated calcium channels and calcium flows in. Calcium influx is what triggers the contraction of the heart muscle cells. So in skeletal muscle, it's the depolarization that triggers the calcium release from the SR. But in heart muscle, it's the calcium entry that triggers the calcium release from the SR. It's called calcium-induced calcium release. So this is one of the key differences between skeletal muscle and cardiac muscle. Cardiac muscle, the calcium entry through the voltage-gated calcium channels triggers the calcium release from the calcium release channels of the SR. In both cases, the calcium goes up, calcium binds to troponin, cross-bridge cycle, contraction. So this is when the heart muscle contracts. Eventually, the calcium channels inactivate and potassium channels activate, and we get repolarization. And repolarization is going to allow the heart muscle to relax. So I think what I'm going to do now is stop and answer questions for the next, I don't know, 4 or 5 minutes. But again, I'm available in lab tomorrow night, in lab Friday afternoon, via email or via Zoom Thursday during the day, Friday in the morning, to answer your questions, both related to the problem set and related to the quiz that is due on Sunday. I know I've covered a lot of ground, and even covering a lot of ground, I didn't cover everything that I wanted to cover, so I'll pick up here on Monday.
So the information until now, it's going to be covered on the quiz.
The quiz is going to cover anatomy. So the quiz, your source of information for the quiz is the, well, let me double check that. Hold on one second.
Okay.
I'm going to stop sharing my screen, and I'm going to look at my quiz. I will make, so the quiz will mostly be anatomy, and the physiology that's on the quiz, there will be some physiology on the quiz, and it will stop at this point. I will make sure that it does not ask you a question that comes after this point in the PowerPoint.
And is the information for the quiz what we learned like right now in the Zoom session, or all the things that we've covered will be fair?
The quiz could cover everything that we've talked about on Monday and today up until this point,
Okay.
plus the anatomy that you have studied or will study from the coloring book, and that we will cover in lab tomorrow and or Friday, depending on which lab section.
Is the anatomy basically the heart? Like, what else could we have from the anatomical point?
I think it will be the heart.
Okay.
We will not, I will not ask you questions about arteries and veins.
Okay, thank you.
And would that include the electrical conduction pathway and the pacemaker as well, like the SA node and
So I did cover the SA node, so I think I could quiz you on the SA node. I did not cover the AV node and the electrical conduction pathway very well. So I would not quiz you on the pathway from the AV node throughout the whole heart because I didn't cover that very well yet. But I could quiz you on the basis for the action potentials in the AV node and the basis for the contraction of atrial or ventricular myocardium, because I think I did cover those, but I didn't cover the electrical pathway well yet. And so I would not quiz you on that.
Could you re-explain the whole calcium thing, release, induce calcium?
Okay, let me try. So the main thing that I want you to understand is that in skeletal muscle, the thing that causes calcium release is the voltage sensor in the T-tubule that undergoes a conformational change and physically opens the calcium release channel. In cardiac muscle, the thing that we call the voltage sensor is actually a calcium channel in the T-tubule. And so the calcium channel in the T-tubule allows calcium to flow in through the T-tubule membrane, and that calcium influx through the T-tubule triggers the release of calcium from the SR. So in skeletal muscle, the voltage sensor is just a voltage sensor, and it physically tells the calcium release channel to open and release calcium. In cardiac muscle, the voltage sensor is actually a voltage dependent calcium channel. When it opens, calcium flows in, and calcium triggers the calcium release channel to open and release more calcium. So in cardiac muscle, so in skeletal muscle, 100% of the increase in calcium that causes contraction comes from the SR. In cardiac muscle, 90% of the calcium that causes contraction comes from the SR, and the other 10% came from the voltage-gated calcium channels that triggered the release of calcium from the SR. Did that answer your question, Sophie?
Yeah, thank you. That makes a lot more sense now.
Okay, yeah. So I feel like I'm mindful of the time. I know some of you have athletics to go to at 4 o'clock. My voice is starting to give out. So let's stop here. I will pick up on Monday with the material on the lecture. I will make sure that the quiz only quizzes you on materials that we covered so far. And once again, I'm available to answer questions by email or by Zoom between now and then. So I'll see some of you tomorrow night, and I'll see some of you on Friday afternoon. And as we work in the lab, I'm also available for questions in or around, the lab. Okay, so happy studying, happy learning, and I will see you, some of you tomorrow night and some of you on Friday afternoon. Bye, everybody.
Bob, I wanted to ask you real quick, if you mind if I, go ahead.
let me stop recording.
Okay.
Let me,